I think it has slowly time to start. If the last people find their places. Kuuluuko? Okay, so I'm just using the mic right in my mouth, so then it works. All right, so welcome to this edition of the Helsinki Distinguished Lecture Series in Future Information Technology. And I know that I have promised that I have retired from this job and you won't see me here anymore, but this was such a special occasion having the head of Google Research New York, Dr. Corinna Cortes as a speaker, so I decided to come here one more time. Okay, so about our guest, Dr. Cortes received her master's from University of Copenhagen and Ph.D. from University of Rochester. And prior joining Google, Dr. Cortes worked at AT&T Bell Labs for a period. And the reason I'm particularly happy to welcome Dr. Cortes here is that we have both kind of very high impact work in basic research and also innovative applications in one person. So about this basic research side, so people that are in machine learning definitely know about support vector machines, also known as SVMs. So Dr. Cortes was one of the founding researchers on SVM research, and together with Professor Vladimir Vapnik, Dr. Cortes received this Paris Kanellakis Technology Award in 2008 for this work on support vector machines. And so SVMs really are nowadays a standard tool in the machine learning toolbox in modern data analysis research. So it's really used in countless applications nowadays. And also this SVM research sparked this kind of explosion in research in kernel methods, which is nowadays a very diverse field in machine learning and still flourishing after 2 decades after the introduction of SVM. So this is the kind of the basic research side. I'm happy to have Dr. Cortes here for. But then the other side is equally interesting, if not more, for the wider audience, are the innovative applications of machine learning that are being researched at Google. As we all know, Google is really one of the main drivers in intelligent applications of machine learning at the moment. And today we will get a peek at these technologies and applications that can rely on this machine learning technology. So without further ado, I suggest you join me in welcoming Dr. Cortes to give this lecture.
Is this working? Now it's working. It has a green light. It's very loud. Can I get it a little bit? This might be better. Okay. Thank you so much for the introduction. That was really nice. Just as a little side story for the SVMs, for all you students here in the auditorium today, I want you to know that SVMs we actually did not think would become anything big when we developed that. It was a remote chapter 4 in my PhD thesis. So maybe there's hope still, you know, write your thesis. It could be the material that you don't know will be that well read is actually becoming very popular down the road. Anyway, it's scratching, yes. I'll be quiet until it stops scratching. I hope you have nothing else to do for the next couple of hours, because I'm afraid I brought with me way too much material. But the good news is that it's not going to be one long lecture on one technical topic. What I'm hoping to do today is to give you an insight to some of the applications and some of the technologies, some of the algorithms that have come out of my group over the last many years. I've been at Google now for 10 years, which puts me seniority-wise in the 99.9 percentile of the full-time employees. I'm one of the old-timers there, maybe also age-wise. I call this talk Searching for Similar Items in Diverse Universes, because you will see different modalities for which we are doing search within Google. So let me start out by actually stating something that is sometimes overlooked, but Google is first and foremost a search engine. It is our job in response to a query to return relevant, related, or similar items in web time that is less than 200 milliseconds. We may be selling ads on the side, and that's how we make all our money, but we are first and foremost a search engine, and we better be good at it or we'll lose our advertisers. Now, relevant items, that's something that the information retrieval community they're dealing with, and I'm not from that community. I'm a machine learning person, so what you'll hear today is something about how we find similar items, how we do it effectively and efficiently. So let me start out by giving you an example for similar search. A couple of years ago, Google bought a company called Like.com. We rebranded it as Boutiques.com, but today it's completely integrated with shopping at Google. Actually, you can try to type Like.com in your URL bar, and it'll translate into shopping at Google.com, the same for Boutiques.com. The idea is here you can search for fashion by using similar clues for visual objects. So maybe you start out with this knitted dress, but from there on you do visual restricts on the silhouette of the dress, on the color scheme of the dress, and you can browse through similar dresses all the time saying, I want more like this. You can, if you have uploaded music to Google, you can get recommendations for similar music, or you can get recommendations for videos based on the videos you have already watched at YouTube. So as I said, these are different modalities at Google. You can search by voice, you can search by video, you can search by image, you can search by shape. And what I'm going to tell you here is something about how we make these applications run. My talk is going to fall in 2 or 3 parts, depending on how you look at it. First, I'm going to be talking about if we have a similarity metric already, how do we make an application that actually flies in web time? Secondly, I'll be talking about how do we generate good similarities, because if we don't have good similarities, we're not going to return items that you find are interesting. Then I have a second part of the talk, because the first part of the talk relates to when things are in metric spaces, that we represent items with a long feature vectors, and we can talk about maybe an inner product between 2 feature vectors. But sometimes that's not the kind of similarity that we have. Sometimes all our similarities are based on graphs. Users, they clicked on 2 items within 10 minutes. We don't actually have a distance between them, but we have co-clicks or other co-occurrences that can form a graph over our space of items. And how can we make use of that very sparse graph to still find interesting, relevant, similar items for you. But let me start out with within the metric space, and let's build an application together. The very first similar item application we built at Google was for image browsing. So let me walk you through the steps that were used in this first application and show you how we took it to what you see today. So here we have two images, New York and Helsinki. And the images may be represented by some very long, dense feature vectors. We're not using just the pixels. We have done something smarter than that, because otherwise we would really have very, very long vectors. An image today is probably 700 by 700 pixels long, and it's not very robust if you rotate the image a little bit. So we use maybe other features, SIFT features that are robust for shape invariances a little bit, color features. Whatever we use, we end up with a feature vector representing the Empire State Building and a feature vector representing, what is it this building is called? Somebody must know. The White Church. Okay, good, good, good. Oh, there's so many foreign students here, right? You know, okay. So here we have the two feature vectors representing these two images, and what we obviously can use as a similarity between them is that we simply take the inner product between these two images. How can we build an image browser based on such a simple metric? Well, the simplest thing that we can think of doing is that, okay, a user comes with a query word Helsinki. Right. What we're going to do is we're going to go out and get about a couple of thousand web pages that mention Helsinki. And we're going to extract all the images in those pages. Then we probably are left with about 1,000 images. Now we can compute, we can construct this feature vector for each of the images. We can compute the inner product between them, and we can start growing a clustering bottom up, right? We cluster together the images that are the most visual similar according to this metric. And when now a user come in with the query of Helsinki, we may cut this cluster tree at some appropriate level and present that back to the user, right? Very simple application, and this is exactly what we did. Here we have similar images version 0.0 with the query Helsinki. And we have a couple of clusters here that are returned back, and I actually have it up and running. I should have it up and running. I don't really know how I get it back out. So let's just go back out this way, because that I know how to get it working. So I have a kind person that maintains this for me, even though it has been decommissioned many years ago. So this is actually live, and it's running inside the firewall. You have the honor today to get to see a few things that's running inside the firewall. If I could only get this one to show the right display. How do I get to do that? Display. Arrangements. Mirror display. Ay, ay, ay. We're going to get there. Here we go, right? So here we have our and we can drill down on one of these, and we can see what's happening. We can explore it further. We can also say Finland, for instance. Oh, if we could type Finland, it would be a good idea, right? And what do we get back? Well, we get the Finnish flag back. That's a good thing. We get maps back. But actually, if we could only... I'm going to go back to my presentation, because I think that is... You trust me by now. I hope... How do we get the resolution turned down? No, okay. Escape. It doesn't want to do anything now for me. Oops. I think I completely wrecked this one. Okay, I'm sorry. Can you... I think we're going to just go back to the presentation and run it from here for now, because I don't know really what's happening with this. So what you couldn't yes.
Hold on. We'll just put a little bit away and try now.
Okay. We're trying again. All right. So if we had been able to get the display fully working, you would see when you did the query for Finland, then this guy also comes up. Now, who's that? That is apparently some Tom Finland, because the application was built, it's a fashion thing or something like that, because the application was built exactly as I told you, right? They go out and they find all the web pages that mention Finland, they extract the images and they cluster the images. So no surprise in that. Now, another thing that if we had continued with the demo, you would see is that if I wanted to search for Helsinki Harbor, I would come up empty. It'll say this query is not part of of what we're supported here. And the problem with it we run into here is efficiency, right? Because what was done here was exactly what I told you. You type a query, right? You go out and you get all these web pages that have images, web pages that have the query term, you take the images, you do the clustering, you present the clustering back to the user, and you cannot do that in web time, right? You cannot do that in 200 milliseconds, not even at Google with all the computers that we have. So this first similar image browser was only pre-computed, and it only maintained a database for the 20,000 most popular queries. So obviously, Helsinki Harbor didn't make it into this query. And that's not something that we like at Google. We like to be able to give back results for all the billions of different queries that people are searching on. So we have to do something smarter than what we did originally. So what do we do? Well, we cheat. No, that's not what we do. It's called we approximate. It's a kind of word for it. So today you can do image search for any image, and I'll get back to how we do it, and I'll show you how we do it a little bit. But let me tell you something about the algorithms that run behind it now. So what we do now is instead of having a very long vector that represents the image, we actually condensed it down. It's a short vector, say 64 bits even maybe. That contain all the information about our images. We now grow a tree, but we grow it top down. We take all the images in the world, we represent them with these short vectors, and then we randomly project them down. We first find one random dimension. We project all the images down on this random projection. You go over there, you go over there. And we continue building the tree down. So we have a couple of thousand nodes at the end. Actually, every image doesn't just go one place. We cheat a little bit, we spill. So every image ends up being in about 8 to 10 nodes down at the end. What do we do now when a new image comes in? Well, we take that image and we propagate it down the same tree. We get all the other images that are down at this node. And here we can compute some similarity metric. If we have keywords, other metadata, then we use that to change the ranking of what we serve back. But this is actually what we're doing now in order to facilitate an image search for you. And it works pretty well, right? I'm risking that this doesn't work for some reason. So no, I'm going to try something else. I'm sorry. I don't know why my display is acting up today, but I'm just going to bear with me for another 30 seconds, and then I'm going to say, play show directly. No, it still does. How do I disable that it does a presenter view? If I'm mirroring display all the time. But then we have this Is there anybody here who's good at displays? No? Well, my problem is here, if I mirror display, right, then I don't get the full resolution. Okay, maybe I... No, it doesn't work for me. Okay. What I wanted to show you here is that now how it actually works real time, right? Because I did take an image here, but I can't get to navigate this because I can't get to see all the. Okay, we are uploading an image, right? And now we are uploaded an image of this image we have uploaded, and it's propagating down through the tree just as I told you, and this is what we get back, right? So we can actually do it real time. You can upload an image into Google image search, and it'll send it down this tree as I told you, and it'll retrieve images from within that node and serve it back to you. You can further restrict it if you have metadata such that you get more relevant images back. As a side effect of this thing, we also can examine the single clusters that we are getting. We have a couple of thousand of these clusters down at the end of the tree. And let me just give you an example of what cluster 700 looks like. It looks like this. It's just a snapshot, a random snapshot of images down from cluster 700. We can furthermore restrict it to images that mention Helsinki in the caption around the image or on the page. And you would say, what does this have to do with Helsinki? But if you actually drill down, you would find out it's a lot of fashion shows that have been going on in Helsinki. Another cluster 1000, may have a completely different color scheme. It may be more drawings, it may be of a different nature. It's all images that have been falling along the same projection axis as we walk down this tree. And we can restrict that further also to just look at Helsinki, and we'll get probably architectural things that are from Helsinki or the surroundings. Just the last cluster, you see again a completely different color scheme. And here I swear this was a coincidence, but when I subset it to Helsinki for this cluster, I don't know if you can explain that image in the top left corner, because at first you say, what are these naked, half-naked ladies doing there? But if you actually drill down, it's city bikes of Helsinki. So it's your own doing. Okay, so this is how we solve the problem of working with similar images and being able to return that in web time. No matter what image you start up with, you can upload your own image and you can see how fast it runs. Having successfully done that application, we thought, well, now we know everything about doing similar items. Let's tackle the next problem, and that's time series. Can't we just use the same techniques here? We'll have this vector that represents our time series, and we'll project it down. We'll get down to some leaves, and whenever we have a new time series, we want to find similar time series, we do this trick, and we'll come back with something. It didn't work. Time series are very different beasts from images. They have spikes, and they have holes, and you have to focus on other features of them. The reason we got interested in this was for an application called flu trends. I don't know if you heard of that. We had an article in Nature about it. So the idea is here, it's displayed on this image, is actually at the end of the month, the doctors in many countries, they report to a central office how many cases of influenza did we have this month. But this is only reported at the end of the month. We would like to do something called sort of nowcasting. It's just predicting the present, right? Can we, based on query trends in Google, find out what is the actual number of flu episode right now instead of having to wait till the end of the month to find out if we have an epidemic coming out. So here we are trying to find things that are correlated. We have in blue from the CDC, the Centers for Disease Control in the US. The blue is the number of flu cases that they reported at the end of the month. And we have in red the search on Google for influenza type A. So obviously these two things are correlated, so we can, as a proxy, a measure for the current level of flu in the US, use how many people are searching for influenza type A. Of course, there are many other query terms that go into providing a robust and accurate model, but this is one of the query terms that were used to produce the model. Today, it's a big site. It's called Flu Trends, and this is what the current meter is for the flu in the United States. I'm very sorry, but if you try to drill down, Finland is not on one of these things, so you cannot see what the flu level is in Finland these days. Denmark is not there either, I have to admit. Sweden is the closest we can get to, and this is the current flu level of Sweden. We have you see, it's very flat, and we have the historic bars for how the flu level was. We wanted to make this data public, and we have succeeded in doing so. The reason we want to make it public is that we, of course, hope that some researchers out there will find correlations in time series that we didn't know of. Is there the next Nobel Prize in some discovery in correlations for symptoms, diseases, economic trends, who knows what, that you can find and tell us about? So in order to make it public, we had to provide a search engine where you can provide a time series and you automatically, in web time, get back all the time series that are well correlated with the time series that you provided. The way we ended up doing this was different from how we did image search. We did instead something we call asymmetric hashing. We're not the only one doing asymmetric hashing, so let me just tell you how we are doing it. What we do is we chop our M time series into chunks. They are each k long, so we get n over k chunks. Then we cluster the data. We have all these little chunks, and we cluster them. We run a k-means. This is a different k. K-means is just the name of the clustering algorithm. We don't have a lot of these means. We don't want to be a big computational burden, so we have currently like 256 cluster centers. And now we represent each time series in our library of time series, the library of all the searches in Google. We represent it simply by the ID of for each chunk which center was it closest to. So think of, instead of having the time series, you now have a series of n over k numbers. In the first segment, I was closest to center number 14, then number 62, 132, etc., etc. Now, when a new time series come in, what we do is we chop it up also in the same way. We compute its distance to all these 256 centers. That's fast to do. And now we can, using only additions, a lot of them, but only still m times n over k additions, we can find the distance of this new time series to all the time series that we have in our library. That can be done in web time, and we do that. We call it asymmetric because it's asymmetric in that the time series we have in our dictionary, we only preserve the IDs of the centers that it was closest to in the various segments. While for the new time series that comes in, we actually have the correct distance to the 256 centers. So it's asymmetric, and we have the exact representation for the new time series and only an approximate representation for everything in our dictionary. And this is actually what we end up having. That's the URL where you can go and play with finding correlated time series. And I'm going to do it even though my display is not really happy today. I'm going to go there. And this is what you find if you go in with Helsinki. You find So when I type a query word up here, it means to take the query stream for the search queries of the word Helsinki and tell me what is the most correlated with that time series. And you find lyric summer. Down here, if we could scroll down, and I hope we can, you actually have an image of the time series. In blue is Helsinki, and in red is the lyric summer. I apologize for the display, doesn't want to display the full set, but maybe if I did this a little bit, it would get better, but it doesn't seem like. Now you can ask, why do we have these spikes here in 2005? Why was Helsinki so well represented? But I'm sure that some of the local people will be able to tell me that much better. I think there was some sports events, yes? Okay. Now, you can also ask, since we are in Finland, if I take the query stream for Finland, come with a guess. What is the most correlated with Finland? Oh, it's not that big a surprise, guys. Hockey history. And you will find the... there must be some event here where you did really well, right, in 2010. All right, so there's a lot of fun you can have with this tool. One of my favorite things you can do is search by drawing. So again, apologize, but you can sort of just draw an arbitrary shape here, and then you can say correlate. And it'll always turn out that there was something that was correlated with exactly that. I mean, can you just imagine a party game? You know, you draw something and then everybody gets to guess what's the most correlated with this. Here you can actually, I think, restrict to Finland. So you can even say, if I only look at the queries that came from Finland, what was the most correlated with this one? Mika. Okay. It makes more sense probably for you than it does for me. All right, back to. So this is a fun thing. I apologize, and you get to the real site, you'll see the data has not been updated for a couple of months, but an update is in the works. So in a week from now, there should be fresh data. I encourage you to look for correlations there and hopefully find a breakthrough in science. If you find a breakthrough in science, please let me know. Okay, and we go back to, all right, so now I've given you some examples of how we make applications so that they can work in web times when we already have the similarity. So let's switch gear a little bit and say, how do we actually get a good similarity so we can increase the quality of our work? And I'm going to talk about two things, actually. I'm going to talk about an application for YouTube and one for structured data. So let me start out with the YouTube one. Okay, so here we may have that people have searched on something already. They have watched something, a YouTube video. And now you have a set of recommendations for them over to the right, and you have things they click on and things they don't click on. So there are things, obviously, that were more relevant and things that were less relevant. So think of here that data is actually a triplet, a query and a positive example and a negative example, right? For a given query, a given video they just watched, there are positive things and there are negative things. And what we want to do is construct a similarity measure such that the positive ones, the ones with the plus on, they have a higher similarity measure than the one with the minus on. And actually we'd like to have it with a little bit of a margin, right? So that's all that we say in this one. Now that I might have to use this one, here we say that the similarities of the positive one should be more than the similarity of the negative plus a margin. Before, we simply use the inner product between two YouTube videos or two images as a similarity measure. But what we're going to do now is we're going to try to learn better similarities. So we're going to stick a matrix W in between this inner product. And this matrix W better be positive, definite, symmetric, because otherwise it doesn't represent a metric. So we can just take this equation and we can rearrange it a little bit, putting in that this is for the similarity, we want to have a W matrix, and we get to this expression. So the goal of our learning would be for all the triplets that we have, that this expression is negative, right? Such that all the positive, all the good recommendations, they are ranked higher than all the not so good recommendations. And this is actually what's called the ranking loss. So we pay nothing if the expression is negative, but if it is positive, we get to pay a price. A ranking loss that we use for many of the applications that we run at Google. One of the big tools that we've been using in recommendations is the algorithm called Wasabi that was developed within my group. And what we do there is we say that matrix W is awfully big, right? If the images are thousands by thousands, it's way too many parameters for us to be learning in real time or for real application. So let's instead use a low-dimensional embedding. Let's take this high-dimensional vector and project it down into a smaller space. And here we are writing it in a more general form, that it doesn't have to be a similarity between two identical objects, but maybe a similarity between a text string and a YouTube video. So we take our query and we project that down in a k-dimensional space, and we similarly take our video and project that down in a k-dimensional space. Now we have two matrices, a U and a V, and the goal of our learning is to estimate good values for the elements in U and V such that the ranking loss attains as the smallest possible value. Now I must say that this is usually not the kind of optimization problems that I like, because obviously this is not convex in both U and V, not jointly. It's only convex in one of them at a time. But nevertheless, it has proven to be very effective at doing what it's supposed to be doing, and there's also something to be said for that. So typically, we want to have good accuracy at the top only, because nobody is going to look at search results way down in the result list. You're only going to look at what we are presenting back at the top 10 maybe. So here we have sort of our scale of similarities. We have a given query that's come in, and this is higher numbers and this is lower numbers, and we have unfortunately a misranking, right? You can see there's a lot of negative things that are ranked above this positive one. If we want to emphasize that it's more important that this one gets right than this one down here gets right, it's kind of the same pattern otherwise, but really this is where we want to make sure we don't see any negative examples. It's up at the very top. Then we can put a weight on each of these. We can put a weight that is determined by where in the list that the result is. And these weights, if we want to emphasize ranking at the top, then we make them bigger at the top so we get a higher penalty if we have a negative up here than if we had a negative down here. If we had just uniform, it will correspond to that we care equally much of every element in the list. The only problem is here that we have to be able to estimate the rank of where you are, where a search result is in the rank list. And that's way too expensive for us to compute. We cannot score all billions of YouTube videos whenever we want to do an update in our learning algorithm, so we have to do something smart. We have to approximate. So how do we do this approximation? Well, think of this. Here we have our data line, and here we hypothesize that our positive example is, and here we have these k negative examples that have unfortunately landed above the positive example. Now, in order for us to find out what is the rank of this positive example, what we do is we say, well, if there are k above and m minus k below, then if I sample n times, then the approximate number of elements that I should find above is n times k over m. So now I just continue sampling until I find, so I have my positive example, right? I compute the score for that one. Now I can continue to sample negative examples from all the negative ones, and I score them, and I continue to sample until I find one negative example, one that gets a higher score. From that one, I approximate, so now I have, in n times, I've found one count that lies above my positive example, so I can approximate the rank of my positive examples as m over n. So this way, I can now actually efficiently make use of my algorithm. I pick a query and a positive example, I compute the score for it, I sample until I find a violation, and then I do an update on my loss function, the ranking loss function you saw before, but where I've used these weights to emphasize ranking at the top. Then I do a renormalization of V and U afterwards. This was one of the original recommendation enhancements we made in YouTube videos. Later on, we have enhanced it for diversity also, because in the beginning, we just focused on the very top positive example. But as you all know, we have different things that we care about. Sometimes I care about tennis maybe, sometimes about running. Sometimes I actually care about work. So in order to get a diverse set of results that are recommended for me, we could, instead of just taking one positive example, we could take a set of positive examples and hope in that set of positive examples, they are representatives for all of us, and then run the same algorithm. But now, instead of just focusing on when do I find something that's violating the top positive example, if I have a set of positive examples, I'll look at where do I have the nth positive example. So it's the same algorithm, it's just looking deeper in the list, and it does more update in order to get more diversity into the top scores. But this is actually what now is running as a recommendation engine for okay, yeah, I have hip injuries right now. So what you see is sometimes I care about hips, sometimes I care about tennis. Sometimes I care about, maybe this is my child or one of my children, then Beethoven, they must have been into the music. Sometimes I care about Danish TV shows. So it has actually succeeded in getting some diversity into the results of my YouTube recommendations. But it's a simple Wasabi-based algorithm that's running in there now. Okay. Going back. If I can find out how to go back. No, I cannot find out how to go back. Okay. And I cannot find out how to. Another thing that we have been working on in order to enhance the similarity measure is this extensions of the SVMs. So just in order for you to get a little quick tour of some of these kernel-based methods. So in the kernel-based methods, what we have is often a sample. We have endpoints drawn identically and from a distribution. And what the goal of our learning is to be able to come up with an algorithm that produces a hypothesis H, such that this hypothesis on any future example, as well as possible, gives the correct answer. I'm not actually interested in getting the training examples correct, but it's of course the test examples, all the future examples drawn from the same distribution that I'd like to have a good hypothesis for. So in the kernel-based algorithms, the user is specifying a kernel. It can be a polynomial kernel, it can be a Gaussian kernel. If it's a polynomial kernel, you have to specify the degree of the polynomial. If it's a Gaussian kernel, you have to specify the width of the Gaussian. And it's actually a hideous idea, right? That we leave so much to the user for specifying the kernel, because you can easily get that wrong. So what we have been working on for a couple of years is a meta kernel algorithm where we kind of put a wrapper around the whole thing. So instead of having just to specify one kernel, you specify a family of kernels. You know, I like to use all the polynomial kernels. I like to use all the Gaussian kernels. And now it's the job of the algorithm out of this family of kernels to select some combination of them so that you get the best performance. Now that of course puts a lot more burden on the algorithmic designer than it did before. But that has been some of the problems that have been tackled in machine learning over the last couple of years, and I have been one of the very active in that area. So the biggest advances probably came in the early 2000s, where people at Berkeley came up with a very nice convex formulation of the problem. So what you see here is that instead of having just one kernel, you have a linear combination of kernels, and it's the job of the algorithm to decide on what factors, how much weight should the different kernels have in my final hypothesis. In this framework, they could come up with one single convex optimization problem that solved the whole problem, both the kernel selection and the learning with that final kernel. It turned out to be a very hard problem. Actually, it's an SDP. It has a complexity that's a little bit too much for many of the applications that we're running at Google. So we have always been out looking for a simpler formulation that could take it down to a QP or even less than that. A lot of people have worked on this problem. Unfortunately, despite that it's an appealing framework, it has not always paid off, and many of the result doesn't outperform just taking a similar even weight of the kernels. But we actually came up with a very nice and simple formulation that works very well, where we split it up again. So instead of having one convex optimization problem, now we have two optimization problems. First, we find a very good kernel, and then we apply that kernel for our SVM. So the way that we do it is that we try to construct a kernel that is as closely correlated with the target that we want to represent. It's kind of the same as if you're thinking of a correlation coefficient for normal linear regression, right? What do? You find the coefficient so you get the best correlation, but in order for you to get a computer correlation coefficient, you have to subtract the mean first of the points. So they're simple standard, and we actually took a lot of that framework and just carried it over to kernels, and we were able to come up with a very simple and nice formulation based on this correlation between the combination of the kernels and the target that we want the kernel we want to align with as best as possible is the kernel of the examples, the target labels, and we can compute this combination, then the mu's that go into the linear combination, we can compute that in a simple QP that's only in the size of the number of kernels that we are making use of, and we can show good properties of this kernel. So the reason I want to just say a few words here is that I think it's important, if you're doing research in machine learning, that you come up with some reason for why your algorithm is good. So this is just a little pointed finger to all the people writing papers, because I review a lot of papers, and I'm always out looking for the argument for why is this a good choice, right? And you can come up with whatever reasoning that you want to, but I want to see that it's good from a computational point of view, that it has a low complexity, that you somehow can prove generalization bounds for it, that it's optimal in some sense, no matter what you come up with. But just giving the community one more algorithm and say it worked on this data set, we got to do more than that. Sometimes it may be a little contrived what people come up with, saying that it's good for this and this reason, but I really appreciate when you try to do that. So please, for me, since I have to review so many papers, try to come up with a good reason for why we should select this algorithm. And maybe you haven't still found out what is the theoretical guarantees that it provides for us, but then spend another month or two, think through why is it we actually think that this one works so very well. So these are some of the arguments that we at least managed to come up with for this learning kernel algorithm that we presented a year or two ago. This algorithm is actually also used at Google. So the place that we found good use of it was for structured data search. So we're dealing a lot with tables nowadays. And we have to find out what is a good table and what is a bad table. You can say that's a simple question. You know, when I see a good table, I know it's a good table. But if you just scrape tables out on the web, you will find a lot of crummy tables because most of the tables are actually formatting tables. Or they contain just long lists of logs of something. 99% of the tables out there, they don't contain actually information. What do we call a good table? It's something with a header or a row or columns, you know, items in it that have real information. So we had to find, as a first thing, in order for us to apply table search within Google, we have to find a classifier for what is a good table and what is a bad table. And that's actually where we ended up using this algorithm, and again with the hope that the display will at least do something meaningful. I'll show you. You can go to Research Google Table Search, and there you'll find our table search, and you can, for instance, input Finland lake fishing, and you will get tables back. And I just want to show you that we can also. Now, the tables, they are not very meaningful if you just have long list of everything. So we want to import the data maybe and make a visualization. This is another part of the team that's working on this. Here we have imported the table into Fusion tables, and we can take a lake here and we can say, we want to say that lake is actually a location, and we save that change, and then what it does then is that if once we specify that this is a location, it's going to try to geomap the location. So nothing is perfect, but let's see where it found out how to put these lakes in Finland. Maybe they didn't put all of them in Finland. It happens that things, they end up outside Finland. Okay, so let's see here if we move over. Here we actually have the lakes and it put them in Finland. And we can get to, I hope that this is the correctly placed. All right, so the machine learning here is first and foremost in finding out what are the good tables and what are the bad tables, but then we put a lot of applications on top of it, and this is one of them. You can do a table search, you can find results back, and you can relatively easily actually get to see them in a meaningful way. Okay, and you can look for other things like speeding rings. This tool is also part now of Docs. I don't know if you're aware of that. If you are working inside Docs, you can get a research panel over to the right, and you can do query search over there, and you can get tables that you then automatically can integrate into your Docs. All right. Now you've seen a number of the applications that I have in my group. Just to let you get an idea for the kind of work that we're doing. We're doing more. In the hope of totally overwhelming you with information, I'm just going to quickly also say that sometimes we do things outside the metric space, because so far we've been in the metric space. We all the time represented our objects with vectors that we could do inner products of, we could apply kernels to it. But sometimes this is not the case. As I say, sometimes the only similarity we have for items is that they clicked on the same item within a session, or they did something else, sort of, you would just have a very sparse graph of co-occurrences. If you have a very sparse graph, it's very hard to use that to do anything meaningful for similarities. So the first thing that we actually have to do is to densify the graph. Only if we have a reasonably dense graph can we start talking about clusters, and we can present back to you some similar items. So a lot of our graph-based similar item search, they start out with a densification. How do we do the densification? We use personal PageRank. Personal PageRank, well, you may probably all have heard about PageRank algorithm itself, right? It's based on a graph. It makes use of the link structure. You start out at a node, and at any point of time, you randomly, uniformly, you pick another node that you're connected to, and you jump to that one. And at every point in time, you also have a finite probability of jumping to a totally random node in the graph. If you continue enough jumping, you eventually reach a stationary distribution that'll tell you who is the most connected, and that's the page rank of that node. And that is one of the first things that was used in Google in order to get good search results back. We don't use PageRank a whole lot anymore, but it's still there. Personal PageRank is exactly just like PageRank, except from that you start at one node, and at any point in time, instead of having a finite probability of jumping to something completely different, you have a finite probability of jumping back to yourself. So it's an algorithm you run from each node. Just think of you start a random walk from yourself, and you hop around, but at every point in time, you also have a probability of starting back to your first node. Once we used and have found this distribution for each node, we have if we threshold these probabilities, we have a denser graph for a specific node. And we can then, on top of that one, run a clustering algorithm. We typically use something very simple like a single linkage clustering algorithm. So this is just an illustration of how this personal PageRank may be running in 4 steps, right? We start out with a red node in the middle, and it has some connections. But at every point in time, we have a finite probability of jumping to the other, or we can jump back. So over time, we find out that we can also actually get to some of these other nodes. So in a way, we densify the graph. And if we stopped it after here, the 4th stop, we would maybe cut the blue node off here still, but we have now that we have enlarged our neighborhood with 2 more nodes. On top of that one, so I'm just going to spare you for how the algorithm runs. We run, as I say, a single linkage, often a max connectivity. So we just connect every node with the ones that it has the strongest link to. And that is an algorithm that also, all these algorithms, they can be parallelized the hell out of it. So we can run them efficiently, and we can run them repeatedly in a hierarchical fashion, and thereby get small clusters that we can join together to larger clusters, et cetera, et cetera. How do we make use of this? Well, we actually have a very nice application that's used to organize your images. And it's used to find new places of interest in the world. It is, again, with the risk of everything going haywire, here I'll first show you, if it'll work, a random cluster that contains 10 images. Well, you'll say, this is too simplistic. It's obviously all from the same user, right? It's just different. So we haven't learned anything new here, right? We just found a cluster that's images from one person's album. So let's instead say we want one with, no, let's make it 200. Then I doubt it's going to be from just one user. Let's see if we get anything. If we don't get anything quickly, then I'm going to switch back to the. Come on, Google. This is the back end. This is not visible to the outside. That's why we allow everything inside Google takes longer time. We use all the resources so it looks good on the outside, and we don't give anything much to the internal users. They can just go and make themselves a cup of coffee and talk to your neighbor. And by the time you then get back, then everything flies so quickly nowadays, right? With all these computers. No, it doesn't. It doesn't want to do anything quickly here. Oh, here it came with something. Wow, we did see. God, I have no clue what this is. But it is obviously a place of interest. And it's not from the same user. You can see that here we have with flowers around, and here we have some person in place of okay. So this is some of these clusters that we are discovering, and I can now show you. Come on. A lot of these clusters that we have been discovering. And the idea is that when we have discovered these clusters, then we have obviously identified entities that people out in the world, they care about. More than one person cares about it. And we are trying to, just as many other search engines are doing, we are trying to build a knowledge graph of the whole world, right? So these are probably places of interest that we should add to our knowledge graph. So we automatically can tag any image that we see on the web with that it belongs to this knowledge entity. So Finland, we found nothing of interest in Finland. No, that was a cruel statement. It's just because I'm zoomed out, okay? See here, we have plenty of things that we found about Finland, right? What have we found up here? Oh, we have found a landmark. If I could, let's a replot bridge. It won't let me scroll, unfortunately, so you can't get to see the picture of it. Let's take something further down here. Do you know what this is? It's yeah, there you go. Well, we can try one over here. That looks like also a nice. We don't know the name yet. It's just called Center, right? We still have work to do. Probably if you click on more info here, then you'll see that we have work to do. Well, I mean, all we've done so far is we have identified clusters that are probably of interest to a number of people, and it's now our job to enrich our knowledge graph with this information so that once you've been to and visited this place, you upload your image, we'll automatically be able to tag that this belongs to this entity, and we'll be able to give you information about it, such as when the building was built, or what town it's in, and how many people live there. KG means knowledge graph, right? So we're trying to enlarge our knowledge graph. Okay, I think I've said enough. So I think I should definitely let you go. Well, anyway, what I tried to do here, and apologies if you got lost in my display from time to time, but so did I. I don't know why it doesn't work. But I'll be happy to show you things if you come down afterwards. What I tried to give you an insight to is how we make these applications fly at large scale. How we make them run efficiently. That is, when we have a similarity measure, how can we actually construct applications that can return results in less than 200 milliseconds? And if we don't have a good enough similarity metric, how can we enhance it? Whether we want to learn it based on triplets that are something I clicked on and something I didn't click on, or whether we want to use some learning kernel techniques for it, the Wasabi or the learning kernel. There are a number of ways we can go around getting better similarity metric, because if it's garbage in, it's garbage out, so we got to start out with a good similarity metric. What I also show you here at the end is that it's not everything that has to live in a metric space. We also try to construct applications based on graphs. And we have tons of graphs at Google. So there are lots of work for you to do. We haven't completed it, far from. Actually, there's one big area that I haven't seen much work on. That is, how do we learn the similarity metric, or the weights on better ways of learning the weights in the graph, so that when we run our clustering algorithms based on our enriched graphs, that we get good clusters. I haven't seen much work on that. There's also lots of other work to do, even if we go back to the metric space, because so far we have focused on similarities, but there's a lot more to be said for dissimilarities, right? And what is, in my case, I want to smooth out the little spike, so my time series, I say that was just an artifact. It was because they had the Olympics that year, you know. I don't really want to see that spike. But one man's spikes is another man's data, right? One man's outliers is what the other person needs in order to find similarities. So how can we find the outliers and use to match on those instead? Or how can we match and broadly say, you know, I like all these shoes or whatever it is, but they're kind of similar, but these have higher heels, or these dresses, they have a little bit longer sleeves, right? So we broadly match on similarities, but highlight the differences. We don't have good measures for these things. So I think actually there's lots of important work still to be done in order for us to make truly good applications for everybody to use. So please go back and do a lot of good work and try to justify with the algorithm if you can. And then I hope that you'll graduate and you'll apply to Google because we need your help. So thank you for coming today.
Hello? Hello?
Hey.
Hello? 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 Hi. Is okay for you?
I can hear you.
I have a question. I wonder why SVM is so popular. To my understanding, SVM and the logistic regressions are both linear classifiers after all. We can make it nonlinear by using kernel or by using a feature mapping function. But after all, in essence, they are both linear classifiers. And in my own experience, I found these two classifiers usually give you the same classification accuracy. But logistic regression is easier to train because the loss function for logistic regression is differentiable. But for SVM, it is not. I'm not sure it's correct. And also from what I heard, in big companies like Baidu, logistic regression is preferred. But SVM is very popular. Everyone talks about SVM. And I wonder how to explain this. Is this simply because SVM is fancier or something?
Okay, SVM is not just fancier than logistic regression. It's a completely different beast from logistic regression. Logistic regression you'll typically use if you want to get a probability measure out at the other end. And SVMs are never tuned to do probability estimates. They give you a distance from a margin, and that's it. So they are used in different scenarios. SVMs is typically for two-group classifications, while, as I said, logistic regression might be for probability measurements where you want to predict click-through rates or whatever you want to. That your SVM is giving the same performance as your linear classifier. I think you can. Well, of course, it will do that for certain tasks, but if you have a lot of data, you can often afford to use a more complex kernel, and you will, in most applications that I've seen over the years, get a better result with a second-degree, third-degree polynomial than you did with your linear classifier. Yes, the SVM is not differentiable in 1 point. In 1 point, sir. Otherwise, you have a perfectly fine gradient, and it's a very nice QP. So the reason that SVM is very popular is it's a convex optimization problem. Your logistic regression is also a convex optimization problem. Your neural network is not. It has a lot of efficient implementations, and it often gives very good results. So I think that's 3 good reasons for using it. I can give you many examples where it outperforms the logistic regression if you just want to do the linear. But remember also, in many of these applications, actually, whether you use a logistic regression, what you do is you expand the features. You simulate to do the kernel expansion. You do it the expensive, hard way. You explicitly go to feature space by using conjunctions of features. So that it's not very efficient necessarily to train your logistic regression.
To my understanding, kernel
It is very scalable. There are many very efficient implementations of it. You don't have to compute the whole kernel matrix up front. You only have to keep track of the ones that you have in your active set, which is the ones that are your support vectors. And you have today many stochastic gradient approaches to training. I can recommend for you, you look at Chi-Chen Lin's SVM package. It is very well implemented and runs very efficiently.
Thank you for the talk. Wondering about the infrastructure that you use to compute your machine learning models. I know MapReduce is something that came out of Google, and I've heard of other frameworks like Dremel or Pregel or these type of things. So maybe my question is MapReduce still sort of in the mainstream of frameworks that you use at Google to compute these models, or do you have something more intelligent?
We have a lot of things that are more intelligent than MapReduce. MapReduce is so simple. But nothing beats MapReduce probably when you want to just talk about efficiency. So a lot of it is still done in MapReduce. I think the biggest advance that has been for training things efficiently has, however, been in doing the stochastic gradients instead of the batch method that we used to do. So in the stochastic method, you just take one example at a time, and you see if it's correctly or incorrectly classified, and then you do a gradient stamp if it's not correctly classified. But I'd heard, yes, there's going to be a lot of MapReduce still at Google. Pregel is primarily for graph-based, and it's actually so there. That's actually a disadvantage because Pregel is also sort of a MapReduce. It goes in these log phases. It does a computation and then it synchronizes. And a lot of graph algorithms, you may not want to pay that price. You want to develop the nodes individually. So there you may want to do something differently and do an asynchronous update also. So I think that the graph community is moving away from these MapReduce log phases, but a lot of the machine learning is still done and the metric learning is still done with MapReduce. Yes.
If your tree only contains a couple thousand nodes, why would you need to compress down to so few bits? It seems like 64 bits per image is awfully little.
It is awfully little, right? And we don't always go all the way to that extreme, I should say. But you need to do something very efficiently in order for you to be able to search it quickly. It is still, we have billions of images, billions and billions of images. So with the image, besides from the cluster ID, you have a lot of metadata also. You have the caption data, you have other words that were used around it. But the cluster ID restricts the search, so you at least only have to search in one of these, a couple of thousand. So you've taken off at least 3 zeros in your computation. That makes a difference.
Okay, can you hear me?
Yes.
Okay. If I remember well, at the first part of your presentations, you mentioned that you split the data based on their projection onto random lines.
Yes.
How exactly do you split the data?
I'm not going to say you everything. No. there are two things, right? You want it to be reasonably balanced. So you do, at heart, you do a PCA, principal component analysis, to find the dimensions along which you have the most variance of the data. And then you split it and you try to take into account that you want about 50% of the data on each side of it. And then, as I say, we spill a little bit. So if you're close to the boundary, you go down both sides. But it is at heart a principal component analysis. And the rest is random. And I'm very happy to give demos of all the things that did not work too well. I don't know why the display didn't want to let me do things and show the whole picture, but I have lots of fun things that we can play with.